I work for Uber, and I thought that a pretty good first slide would be to have some sort of like claim of credibility. So I'm just going to talk a little bit about Uber and what I'm doing there. So as you might know, Uber is this small startup that you can use to get a ride, but not in Austin. And at the company, we actually are very heavily focused on microservices. So right now, I think the most recent numbers is that we have something over 1,700 microservices in the company. And rumor is each time we hire a new engineer, we have like 3 more microservices pop up in production in a little while. And at this scale and at this fan out, it's very important that the performance of each of these microservices or any component actually should be top notch. It really matters. The team I work on specifically actually is a part of this effort because the team is called observability, and what we do is that we provide other engineers in the company with tools to have insights in whatever their code is doing right now. That includes metrics, that includes, for example, request tracing, and there was a workshop about request tracing for Uber, I think on Tuesday or Monday, something like that. The part of the team I'm in, we built a metric collection engine, which is actually not one huge Go service, but a bunch of Go services. And these services are very CPU and memory intensive. And when I say that, I mean it. Because, for example, the request rate for ingestion is something along, like, I think, 9 or 10 million requests per second for ingestion, for metric ingestion. And the request rate for queries is a little bit lower. It's maybe something about around 500-600 requests per second. But the amount of data that the users query from our system is insane. And last time I checked, which was 2 days ago, was something like 75 years of time series per second queried. So one thing about this talk is that normally I do technical talks, as in like, here's a bunch of gibberish, here's some source code, here's a demo in a console, okay, thanks, bye. But this time I figured that maybe I should do something else and make it more like a fake philosophical talk about some things that I find interesting in software engineering. So I might miserably fail as well, because this is the first time I do this kind of talk. And also, when I was rehearsing this talk in front of the mirror a few times, it kind of struck me that when I do this and try to push my like opinions and views out, then I kind of look like this a little bit. So I figured that maybe I should just rename this talk on the spot, so it's no longer wishful thinking. Now it's going to be 28 signs of the end times. So anyway. What I usually like about talks, public talks about computers specifically, is when people first present a problem statement. It's not like, what are we going to talk about? Is there some issue we're going to talk about? Something like that. So I also like this approach. So the problem that we're going to talk about today is complexity, and the fact that the human brain will do whatever in its power to avoid it. And the complexity that we are going to talk about today is the complexity of computers, because it's a conference about computers and software. So yeah, things are complicated, and they are getting more and more complicated with each day, month, year, and with each new release of new hardware, software, or whatever. And if you take a look into a modern computer right now, into a modern server, for example, you would notice that it's actually a marvel of engineering, and it's extremely complex. For example, if you take a look at the modern CPU, then it probably will be something like a chip with multiple cores on it that has multiple deep hierarchies of caches and some very sophisticated execution pipelines. And the code that you run on this computer, on these CPUs, will be pre-processed and split into different things and reordered. And there's going to be a lot of weird things happening inside the processor before it actually executes your source code. And the consequence of that is, even if you run the same code on the same CPU, like 3, 4, or 10 times, then you can observe absolutely different latency characteristics for caches, for example, or different memory access patterns, that kind of stuff. And Fortunately for us, hardware manufacturers actually provide us with tools that we can use to kind of inspect and get insight into whatever is going on there. But absolutely nobody in the world uses these tools except maybe Brent Gregg from Netflix. And I also recommend you to watch his talks because they're pretty awesome. But, okay, to talk a little bit more about that, I have created this wonderful diagram. So, what do you think this is? Any versions? You can say it right from the spot. No versions. Okay, so I'm going to put some labels on this diagram and make it easier to understand what the hell is going on there. So how about this? Now it kind of starts to look like a part of a data center, like a small portion of a network. We have like 4 servers. These servers are probably in the same rack. They are connected with some fast network so that they can talk to each other. They probably have some sort of storage attached to them. Some of them might have an SSD inside the unit. Some of them can have, for example, a serial attached CASI or something like that. And this rack is probably also attached to some router, some backbone networking infrastructure in the data center that provides them with shared services. Maybe it's like a tape device for long storage, or maybe it's an uplink to the outside world through the ISP, or something like that. And it kind of looks like this in more or less all data centers, but like scaled out, and it's not 4 servers, but maybe 40,000 servers or something like that. But what happens if I replace all these labels but keep the picture the same? How about that? It's the same picture, same color, same shapes, but now we can see that now it looks like actually one single server. We have 4 cores. These cores are connected to each other with some pretty fast interconnect. It can be QPI, it can be hypertransport, depends on what CPU vendor you're using. These cores have memory banks attached to them, and as you can see, different cores have different memory banks attached to them. And they are connected to a peripheral hub that provides them with shared services, which can be, for example, a SATA disk that they can use for persistent storage, or it can be a network adapter that gives them access to the outside world, internet, or the rest of the data center. And the thing that I want to point out in these pictures is that when we develop software, when we architecture, when we plan the architecture, when we try to build something, some distributed system, for example, and we look at this picture, which is the data center, we really do care. We want to identify and acknowledge potential problems, bottlenecks. Like, let's say we build a distributed storage, right? We look at it, we look at the design that we have, and we think that, okay, so what can go wrong in this picture? So what happens if the interconnect between servers fail? Oh, yeah, we have to take care of that. Oh, what happens if the link between servers and the router gets congested and we can't reach the other racks, or we can't reach the internet? Oh, that's a problem. We have to take care of this. Oh, what happens if, for example, the data that we want to access is attached to a storage which is attached to a different server? Well, that's a problem because we have to go through the network back and forth all the time. And there are more and more of these kind of problems, and there are a ton of papers about it, about how we can solve it, about what are the workarounds, and that kind of things. But when it comes to one server, for some reason, all of this immediately disappears. When we build a single piece of software, for example, one of the nodes, one of the instances of this, say, distributed storage, we don't care at all. Like, oh, there can be congestion between cores and PCH so that we can't write data to disk and read from network at the same time. Who cares? Whatever. Oh, there is a link between cores that is used for cache invalidation and memory access when the memory is allocated from a different memory bank. Whatever, who cares? Oh, there may be some latency between the cores and the peripheral hub, or maybe there is some latency between different memory banks and different cores. Well, nobody would ever care about as well. And that's pretty weird to me. And I've seen this behavior a lot of times in software engineering, and that is basically what I was going to talk about, and what I'm going to talk about now. And the thing that kind of strikes me as an interesting example is that we sort of understand that this is more or less same thing, but scaled out and scaled in. But we don't want to think about the complexity when it comes to one single machine and how this complexity interacts with other machines in one data center. And this sort of triggers a kind of a cognitive dissonance in our brains. And as engineers, we don't like this kind of feeling. We don't want to have cognitive dissonance or whatever. So we really try hard to come up with workarounds and solutions and ideas how to overcome this kind of complexity. And one very common way to do that is something that can be really perfectly outlined by this quote by David Wheeler, which is, all problems in computer science can be solved by another level of indirection. And this is exactly what we do all the time. So what we did as a community, as an industry, is that we took this complexity that is inside every machine, every server, and every computer in the world, and we sort of compartmentalized it. We divided it into domains that looks like this, so that we don't need to think about the whole thing at the same time. We can just think in our own tiny little domain, and if there is some complexity or problem, we can just push it down the stack because somebody else probably has already taken care of it in some other layer of this wonderful pie. So for example, as an author of some piece of software, like I don't really, for example, I'm writing some sort of a web service, right? I don't want to think about how HTTP is implemented, so I just delegate it down the stack to the framework, which there are plenty of these. If I am a framework author, I don't really want to know how networking works and how packets go around the internet and whatever, so I just delegate it to the language runtime, which should take care of this probably. If I'm the language runtime author, I'm like, well, I don't really need to know how all this like hardware things works and how the memory allocation works, so I'm just going to delegate it to the operating system runtime, which is like glibc or something like that. If I'm the glibc author, and so on and so forth, and basically we just push it down the stack further and further away. But the thing is that we're still smart people, so we still know that this thing still exists somewhere there. Like there are still drivers and firmware and kernel and all this kind of things that still are in our computers, and it's sort of like something in the corner of the eye, and we still have to think about it. So as good engineers, we made another step, and we invented something I call the great black box. So a great black box is a thing that we can use to put all the things that are oh, it's even better. Anyway, a great black box is a thing that we can use to put all the things that we don't want to think about away and forget about and pretend that they don't exist. And because we are engineers, we decided to start with something that really annoys us. And this something is the real world, or the physical world. So we invented this. We decided that actually hardware is not a thing anymore. Servers just float in the infinite space and work somehow, but we don't need to think about it anymore because it's pretty cool. But that wasn't enough, so we decided that there's no servers anymore as well. Servers don't exist as well. Now we have containers. They also sort of float in the infinite black space, and they execute our code somehow. We don't really know how exactly, but it doesn't matter, and we don't want to think about it, and we put it in the great black box. But that wasn't enough. There is no containers now too. We don't have any containers. Now we have just the platform. Platform is an abstract thing that we can call into, and it will do things for us. Like we want to get a request, well, it just comes from the infinite black space as well, and we can just handle it and then send a response back to something, and something will handle it, but it doesn't matter. We don't want to think about it. But that wasn't enough. So now we have the framework as a service, which is like platform, is also now in the big black box. And we don't want to think about this kind of things. Now we have only the framework, our favorite one, which I don't know which is your favorite one. And we can just call our framework, and then there will be some platform maybe or whatever, and it will just handle all the things for us in this great black box. But that wasn't enough. So now we have serverless, which means even the framework doesn't exist anymore. Now we just need to write our code and deploy it somewhere, and it was just going to float in this infinite black space and execute by magic, and things will just work somehow. But we don't want to think about it because it's complex, so we're just going to put all of this into great black box and forget about it. I'm going to predict the next step, because serverless is just right now at the doorstep. This is the hotness. The next step, I call it clueless. Everything is a huge black box, and we have no idea how it works at all. So I really don't want the industry to move into that direction because I think it's not really that good. So I'm going to show some benchmarks out of nowhere. The thing that you can see at these benchmarks in this graph is something we did in Uber when we realized that there are a lot of things with the resources and the hardware we use that we can do better. And it's not a big gain. It's probably something along 10 to 15% gain in all of these different graphs. But the thing I want you to note about this is that all these changes were made without, all these improvements were made without actually changing any code at all. It was just trying to utilize the hardware better by understanding what the hardware we actually use, what it is, and how we can better sort of plan our deployments and better schedule our deployments and better use the things that, that we have, our actual physical world. But anyway, that was the problem. And now we're going to talk about the solution. And I put solution in quotes here because it's not actually a real solution. And to do that, I want to introduce a fictional character, Donald the engineer. It's a fictional character. I don't know why you're laughing. So the thing about Donald the engineer is that he is the same kind of engineer as all of us. That means he is really good at one thing, and that thing is not writing source code. This thing is avoiding work at all costs. And we all love that. We just admit this. Nobody wants to do anything. So, and this approach to software engineering can be summarized in this quote by Donald the engineer, that somebody else totally did a tremendous job already. And let's imagine, for the sake of this, this exercise, that Donald the engineer decided to start a project, to write a database to store all the personal data of all the people. And as any other engineer, Donald doesn't really want to care about things like memory management, like CPUs, cores, networking, whatever. That's all very complex and hard. So what Donald the engineer is going to do is that, for example, since he knows that database, one of the properties of a database is that it consumes a lot of memory because it wants to keep all the data close so that it can serve the user request faster, that in order to do that, he'll just pick some language and we'll just call the memory allocation function and allocate all the memory he wants and just put data into it. And that's it. So let's say, again, for the sake of this exercise, Donald the engineer picked C++ as his language of choice to write the database he's willing to do. And this is basically where it all goes wrong from this point. So in order to do that, in order to write this database, in order to allocate memory, in C++ you call a function called new. And this function just takes some type or something like that and just gives you a pointer to a newly allocated memory that can fit the object you want to put in it. So still, we don't really want to think about how this memory is actually allocated and where it's coming from, what memory bank was it allocated from, what core is actually working with this memory, what is the latency characteristics of this memory, how it will be laid out in cache, and that kind of things. We don't want to care about it because we have the next layer of abstraction. We have this next layer of the pie. We have, in case of C++, it's going to be libc, which is the language, which is the operating system runtime library that takes care of things like syscalls and memory allocation and all this kind of stuff. So we're just going to call new, going to call malloc. Malloc is a function that is a part of libc, and apparently malloc will take care of all these very complex details. But surprisingly, libc was also written by software engineers who are really good at avoiding work. So if we take a look into libc source code, we will see this comment, which basically states that libc actually doesn't care about any of these things. libc doesn't care about things like hardware layout, how to allocate memory from proper nodes of proper NUMA nodes of your server, do basically anything at all, because there is somebody else who probably took a really good job of it. They took a really good care of it. You might say that, well, you pick C++, that you're kind of crazy already. Nobody picks C++ if you want to avoid work at all costs. Okay, we can pretend that instead of C++, Donald the engineer actually picked Golang, which is the fancy language that everybody uses for everything at this point in time. So surprisingly, Golang was also written by software engineers who are really good at avoiding work at all costs. So if you look at the source code for Golang, you might see this, which basically says that Golang actually doesn't care about memory management and whatever, and NUMA nodes, this is all very complex, so we're just gonna allocate memory and pull it all together, and somebody else will take care of it. And to explain this, I have another cryptic diagram. So this thing basically depicts, it's like a very crude and primitive depiction of Golang runtime model. So a few things that I want you to note here is that with colors and shapes, I tried to demonstrate that these three things, the red, the blue, and the green, are completely separated and have nothing in common at all. So the first thing, the circles, the red circles called M, are machine threads. These are the actual operating system threads that Go runtime will spawn to run your code. And the number of the threads can be anything from 1 to like 10,000. The blue things are called Ps. These are processors. Processors are the things that can actually execute your Go routines and Go code. But in order for P to run, it has to be attached to an M. And the number of Ps are always equal Go max procs. I don't know how many Gophers. So a few. So Go max procs is a variable you set that tells Go that I want you to run this number of Go routines concurrently at all times, not more, not less. So the number of Ps is always Go max procs. And also there is a net polar, which is the thing that does all the I/O for you, and there is the heap, which is all the memory that is available to Go runtime, to this specific concrete service. So what happens is that when P needs to run your Go code, first it picks one of the M's, the actual machine threads, to run, and then it runs until there is an event, such as a syscall, for example. And as you know, you do syscalls for everything. Read data from the network, write data to disk, it's all syscalls. So when a P encounters a syscall, it removes the Go routine from an M and parks it and waits until the syscall is completed. So also, all Ps have a cache, which is like a little piece of memory that they can use to allocate small objects. And this cache is filled from the heap, and it's returned to the heap each time a garbage collector cycle starts. So what happens is that a situation can happen where a P is allocated to one of the M's, which is an actual thread that runs on one of the cores of the CPU, and let's say it wants to read some data from the network. So it allocates a buffer to read the data into, and then calls a syscall read, or whatever, receive, something like that, to receive the data from the network. At this point, P is detached from an M and parked. After a while, when we read whatever we want to read from the network, this P wants to resume the execution of the Go code. But this M is already busy with doing something else. So we pick some other M and attach P to this M. But this new machine thread can be on some other core. And this core can be attached to a different NUMA node, for example, to a different memory bank. So what will happen is that we'll suddenly start to run again, and we'll have all our data in the buffer we just allocated. But this buffer is now in a completely unrelated place, which is totally fine. Nobody cares about it. So, okay, I think I cleared that part out. So glibc doesn't care about memory in this example. Golang runtime doesn't care about memory. But we have the kernel, right? Kernel is the bastion, the last resort, the shining beacon of light we all look up to when it comes to really complex things in computers. Well, you won't believe it, but kernel was also written by software engineers who are really good at avoiding doing any work. So this is a quote that comes from, it's one of the issues in the Golang GitHub. And basically what it says is that the GC worker thread in Golang is so good at its job of scanning memory and collecting garbage that Linux kernel thinks that this is the actual work that your program is supposed to do. And it takes all the memory pages and moves them to the core that is closer to the GC worker M, which is exactly the opposite from what you want to actually do. This issue was resolved, so it's no longer a thing, but it was resolved with a hack, because nobody understands what's going on and nobody wants to solve it. Speaking of GC workers, let's imagine that Donald the engineer actually succeeded with writing the distributed storage to store all the personal data for all the people. And he just deployed it to production, and to his surprise, but not to our surprise, nothing works. And it doesn't work because it's terribly, terribly slow. Donald the engineer actually follows all the modern trends in software engineering, so he knows how to use tools to introspect and profile the code. So he runs Linux perf-top to see what's going on, and this is what Donald the engineer sees in the output. It sees that his database spends about 43% of total runtime collecting garbage. This is the GC garbage collector background mark worker go routine right there at the top. Well, that's bad, but not really clear what exactly is going on there. So Donald the engineer flips another tool that he knows about, which is the flame graph tool. And it starts to look even worse than that. Now we can see that the thing that happens is that it's actually something like, I think, 75% of total runtime is spent in garbage collector, in Golang, collecting garbage and scanning objects and marking them and doing all this kind of stuff. While the actual useful work is, what, like 25%, maybe even less. So it is very unfortunate. But do you think Donald the engineer could avoid this by doing something? Well, actually, no, because it's Donald. But any other engineer could have done this by trying to write the code in a friendly way for example, Go runtime, or by trying to understand how memory allocation works, or by not trying to pretend that there is somebody else down the stack that would take care of all the problems that we don't want to take care of. And one thing that is kind of not actually letting us do that is that the languages themselves and all these other layers, they actually encourage this kind of behavior. Like, don't think about things, we'll take care of everything. And for example, this is a quote from Golang engineering blog when they released Go 1.5 that basically says that there will be some future somewhere where hardware will be powerful enough to actually make GC useful for us. But what it basically says, if you translate it from the nerd speak to actual human speak, is that if you're a lazy engineer, get a bigger computer. But unfortunately for Donald, his computer is very small, I mean slow, and it will never work for this case. So this is the last picture I have, I promise. But rejoice, there is a workaround. It's not that bad. The workaround starts with the fact that we need to accept that we are very, very, very terrible, very bad at guessing, predicting, and reasoning about computers. All of us. We are terrible. We cannot do that. Stop. Don't do that. And the only thing we can do is to ship the code that we write, ship the services to the users, and then gather feedback. This is the best profiling tool we can have, and this is the first profiling tool we should use. Ship it to the users, listen to them. This is the only thing that's going to work. And yeah, I can't stress this enough. Everybody is not doing that anyway, but this is very important. And once you gather this feedback, and once you know that your users tell you that, yeah, like everything is pretty good, but when I click this button, it's super slow, can you fix this? Now you know that, okay, so actually I shouldn't optimize these 25 functions that I really feel good about. I should actually optimize this other one, which I don't even want to touch. Or I didn't even know that it exists, for example. And when it comes to this, then there is a bunch of tools that we all should use to make sure that these things this kind of things don't happen. Jerome, you're late. And this is just a short list of things that we all can use to to kind of get insight into what our code is actually doing on the actual hardware with all the actual layers. And different kind of tools provide you insights into different layers of this pie that I was showing you previously. So for example, there are generic tools like the eBPF, which is the shiniest new thing ever right now, and everybody's talking about that. Or there is old Linux perf, which basically will tell you what your code is doing right now. It has a lot of features. It can actually make use of hardware tools that like for example, Intel or AMD is putting inside their CPUs to show you exactly what's going on, and so that you could actually optimize for things that you care about. There is dtrace, who everybody knows that this thing exists, but nobody can use it. And there is Intel, for example, vTune, which is a commercial tool. You can pay for it, but it also provides you a lot of insights, nice UIs, and whatever. There's also one from AMD, but I don't know what it's called. I can't remember. There are language-specific versions of the same tools, like in Golang, there's pprof that will give you more insight into what Golang is actually doing. There's a perfect thing that I forgot to put on this list, which is the Golang's tracer, so that you could actually map what all of your routines are doing right now in sort of like this timeline, which is really useful if you see that something is slow but you don't understand what's going on exactly there. If you use Python, for example, there's Python C profile, and for all the languages there are other kind of tools like this. And there is app-level instrumentation, which is, for example, Prometheus, which is a metric collection framework that you can use to emit your app-level metrics to keep track of things that you care about, which I will remind you, you should first gather from the users, because these are the people who actually care about what you write, not you. There is Jaeger, for example, which is Uber's request tracing framework that I think we open sourced. Yes, we did. Good. And then there are companies that you can pay money to, and they will do this for you, like, for example, Datadog. This is one thing you can do to make things a little bit better. Another thing you can do is this. So as you remember, I tried to, in my first few cryptic diagrams, I tried to show that the computer, like one server, is not really that different from a network of servers. So we can just pretend that it's actually a thing. And we can pretend that each core is actually a network node, like a separate server. And in this case, we can spin up multiple instances of whatever service we want to run and bind them to the node so that they're sort of compartmentalized and bound to one core or one NUMA node or something like that. And then we can put a load balancer in front of this whole thing. And this will essentially allow us to use networking concepts to distribute the load across physical CPU cores in the same way we distribute load across network nodes in a network. And the load balancer will present the endpoint the same way that the users can use the same way as if it was just one instance of the service that you want to run. Obviously, it's not that straightforward. You can't, for example, distribute like MySQL this way because it has storage and persistence and all this kind of stuff. But if you have a stateless service, and in my team in Uber, almost all of our services are stateless except the actual storage, then you can use this technique to easily gain that 10–15% of gain without changing anything in the source code of the services. And even more, you can actually pin different components to different cores to sort of match the topology better of the service that you're using and of the hardware that you're running the service on. So, for example, if you have like a front end and a back end pieces of the same service, you can pin front end on one core, you can pin back end on other different cores so that they don't actually interfere with each other. And there are some architectures where you have actually a shorter path from some cores to, for example, the network adapter. So you can pin your front end to a core that is closer to the network so that it works faster and latency is lower. And again, rejoice. I have good news for you. I actually wrote a tool that does it for you. So this tool, what it does is basically it analyzes the topology of the hardware, of the underlying hardware of the server that you use it on, and then given a container image of the service that you want to run, it will use Docker to spawn the required number of instances of the service and pin it either to the core or to NUMA node or whatever. You can actually select all these kind of things. And then it will set up a load balancer in front of it that would take care of distributing the load among these instances. And it already supports IPVS out of the box as a load balancer to do this kind of things, but it's all pluggable. So if you have, like, if you want to use it and you have something else in your company that, like some other load balancer or just something like Nginx or HProxy, you can easily plug it in, and it will just do the same thing for you using your favorite load balancer. And yeah, using this tool, I got these benchmarks from the beginning of this talk, where we just saved like 10–15% of, we gained 10 to 15% of performance by just doing that. And in some cases, the gain was actually very ridiculous, like 75% more speed just by using this, because we don't want to care about complex things. And that is basically everything that I was going to talk about. Repent or perish.
What are the drawbacks of pinning? Because when NUMA and multi-core chips came out, pinning was also a hack. So.
Well, I think that's kind of the description of the history of software engineering. It's like we just do hacks, and then some hacks become standards. So the downside is that, like, if the thing that you want to pin actually uses, like, heavily uses concurrency, multiple threads, and that kind of stuff, then you will limit it to one core. But this will actually allows you to do sort of like a lower granularity pinning. So you can pin it not to a single core, but pin it to a NUMA node, right? So it will have, like, for example, yeah. So if you have like 24 cores, it can pin. Like, it can spawn 2 instances, pin one to first 12 cores and the other one to the next 12 cores.
You don't need this in prod?
No. I tried, it worked, but it's magic. Production doesn't like magic. I'm an SRE, I don't like magic as well, so maybe later we will use it when we would actually care about money. Any other questions? Doesn't look. Oh no, there is a question.
So, so you said show the progression of where you don't want the industry to go. Serverless.
Yeah.
So, do you have a possible path? Path from there? Or, I mean, your project is obviously one way to go.
See, yeah.
Understanding, but what else should happen in your opinion?
Yeah, I don't actually know. I mean, that's a hard question, and that's a really hard problem. As, like, if you start to think about this in a way like, okay, so instead of hacking around it and working around it, so how can I actually solve this problem? And you start to look into it, and you realize that it's incredibly complex. You can't actually do it like in an easy way. And I think the general trend is fine, because the general population of engineers, they don't actually want to care about this kind of things, and that, like, because we have serverless and infrastructure as a service and platform as a service and all those kind of things, because of that, we got, like, much more velocity in building new stuff and deploying it to production, building new services and that kind of stuff. But I think just the first step that can be done is that we have to just stop and think about what's going on, because we just put more and more abstractions on top of each other. And at this point, like, if you, for example, write a Node.js service, it just looks ridiculous. Like, the amount of layers your request, for example, has to go through until it actually reaches, like, your handler and then goes back to the user is incredible. And I think the waste factor there is maybe, like, I don't know, 80%. You can just remove all of this. And by just doing that, you'll gain, like, a lot of performance out of nowhere.
I think part of the problem is our paradigms of programming systems really have changed as computers evolve. So our languages and our runtimes still think you have one CPU, one core, and threads and processes are just hacks, right? We need something more advanced that can distribute your work around whatever system you have, whether it be the system workers attached to its memory, and it's all like a thing. Right now, they're all, your memories over here and your workers over here, so it's a mess.
Yeah, I couldn't agree more. That's a really good answer.
What language do you think handles this best? I mean, or allows the engineer to be able to
Yeah,
tackle these problems best? I mean, in your opinion, of course.
yeah, that's super opinionated. Yeah, that's basically a holy war trigger right here.
Well, I mean, my opinion is, this is implemented in lots of languages, but I kind of like actor model for something like this, right? So the actor will hold its compute and its memory all together, and if you have a smart enough runtime, then it'll pin it or it'll keep everything together. But I don't know. You might have to have some combination of platform support and hardware support so they work together. Right now, the things are really disconnected. What you write your code in and what it runs on, very disconnected. They may have to get a little bit more connected and exchange.
Yeah, I don't think that such language exists right now.
No.
Like, I made a few examples of Golang as a language which is definitely not that. What it actually does exactly the opposite. It's like, we're just gonna allocate memory and schedule processes, threads in absolutely unpredictable way so that we actually make kernel that guesses absolutely invalid so nothing works. So yeah, maybe actor model is a good paradigm to use it. Maybe there's gonna be a language later. Maybe Rust will evolve into something like this. Yeah, I guess we'll see. I think that's it. Yeah? Yep. Thank you.